Greetings and welcome to a series of lectures in Precalculus Graphs and Functions. This is lesson 2.4, Functions. Let's jump in and start talking about functions. First of all, so we can talk the same language, let's look at the definition of what a function is. A function is a special relationship in which each element in one set, for this example we'll say x, corresponds with a unique element in a second set we'll call y. So for every x, it goes to a unique element in y. Now this x value that we plug in is what's called the independent variable. It's our input value. And the dependent variable is the output value or variable. In this case, x is our independent and y is our dependent because the output depends on what you put in and therefore it's dependent. So let's look at a small function, y equals 5x plus 3, meaning the independent variable is x, the dependent variable is y. Now this doesn't matter what variables we use or the names of the variable. This could have been a here and b here. Independent variable would have been a, dependent variable would have been b. So what we call these x and y, a, b, l, m, doesn't matter. We need to understand that the values we plug in are independent and the values that come out are dependent. Now the values that we are allowed to put in are called the domain. These are our x values in this instance. The values that we get out of it is our range. Now sometimes there are rules about what values we're allowed to put into the equation, the function, and because of that there may be restrictions on what comes out, and we'll look at that a little bit later. Here we go. Now let's look at this picture right here. Here are our x values. They could be a, b, c, d. Here are y values. They could be 1, 2, 3, 4. Now the function does something. It takes an x, manipulates it, and pops out a y value. When a goes into the function, it pops out a 1. When b goes into the function, it pops out a 3. When c goes into the function, it pops out a 3. And when d goes into the function, it pops out a 4. This is a function because every single x goes to one and only one y. Now it's okay if two of the x values go to a particular y value, but as you can see, one x is going to a y. Now looking over here, this is different. A goes to 1, B goes to 1, that's totally okay. But C goes to 2 and 3, and then D goes to 4. And therefore, because C goes to 2 values, this is not a function, it just stays a relation or a relationship. It doesn't get pushed up to the function level because C breaks the rules. Totally allowed for x to go to the same y, but you're not allowed the x to go to two different y's. Therefore, it's not a function, it's a relation. This is also a relation that happens to be a function. This is a relation that's not a function. Now let's figure out for the first function what the domain and range is. The domain are all the values of x we're allowed to put in, and we are allowed a, b, c, d, and therefore the domain is the set a, b, c, d. What pops out? 1, 3, 4. I know 2 is over there, but nothing's pointing to 2. And therefore, our range is the set 1, 3, 4. Because the second set is not a function, it does not have a domain and range. Okay, so here's what's going to be our rules that we follow. For f to be a function from one set, let's just call it x, to set y, the domain of f is the entire set of x's that we're allowed to put in. The range are the f of the function are the set of y elements assigned to an element of x. And right here, 2 was not assigned to any x, and therefore it wasn't in the range. x can go to one and only one y value. So each of the x's went to one y value. Y can come from more than one x. So this one came from a B and a C, but that's totally permitted. This is not permitted where you have C going to two outcomes. The notation is going to be very important for us to understand. How we write things down is our notation. Functions are referenced by a single letter. They could be lowercase f, g, h. It could be uppercase as well. This could have been uppercase f, g, h, q, p, s, t. What letter you choose is up to you. Personally, I use f a lot for function. G sometimes if I've already used f recently, sometimes G, and even sometimes H. And then sometimes I use a letter that talks about or will reference what's in the function itself. So if I was talking about this is the function for velocity of an object, well then maybe I call the function v instead of f. So it's up to you what you use, but it's generally denoted with just a single letter. Then what we tack on is when we reference it, functions are referenced with the independent variable. So f parenthesis x parenthesis. F is the function name. X is the independent variable. G parenthesis a parenthesis. G is the function name. A is the independent variable. H parenthesis m parenthesis. H is the function name and m is our independent variable. Now how we read this is not f parenthesis a x parenthesis. That would just be too much to say, and let's face it, mathematicians are really lazy, otherwise we wouldn't use these symbols for everything. So we read f parenthesis x parenthesis as f of x. Sometimes it's read as f at x. I would say that's harder for me to say quickly, so I say f of x instead of f at x. Just what I say. Okay, so how do we put an equation into function notation? Well, remember, function notation is the name of the function along with the independent variable. So our normal y equals 5x plus 3 will turn into, instead of y, we're going to write the function of x equals 5x plus 3. We just exchange a y for the function at x. Now let's take a look at this. Same example where we have an input of an x and we get out our function of x. So a goes in. The function at a is going to be 1. B goes in. The function of b is 3. C goes in, so the function of c is 3. And the function of d is 4. So this means the input, and once we do things to it, this is our output. Now, keep in mind that sometimes when we see two letters together, we mean multiplication. But in this case, function notation does not mean f times x. It is a function at x, or the function of x, f of x. There are many ways to represent functions. One way is to show it as an ordered pair. So, for example, we have the function f, and that would equal the ordered pair of x comma y. Now, it could be more than one ordered pair. For example, I have the function of g, and it has 3 ordered pairs in its function. So it has, these curly brackets mean set. So it's the set of AB and CD and EF. The good way is we can figure out the domain and we can figure out the range very easily. The first value is the domain. The second value is the range, as long as this G is a function. We'll talk about that more. Okay, so let's determine whether these relations define a function. So we have R is the set of ordered pairs, -1, 2, 1, 3, 5, 2, negative 1, 3. And S is the set of ordered pairs of negative 2, 1, 0, 2, 2, 1, negative 1, negative 3. Let's start off with the first one, the function r. Now, r is not a function because, remember, we're not allowed to double up on the x values. We're totally allowed to double up on the y values. But when you're looking at negative 1, 2 and negative 1, 3, that x value is going not only to 2, but it's going to 3, negative 3 as well. And because the same x goes to two different r sub x values, that's not allowed. And this is a relation and not a function. For b, remember, we're only worried about the x's repeating. We have the x value of negative 2, 0, 2, negative 1. The x values do not repeat, and therefore this is a function. Now, it's totally okay for the y values to repeat. I have a 1, 2, 1, and negative 3. The y values can repeat all they want, but we're not allowed to repeat the x values. And because our x values don't repeat, s of x is a function. Or in this case, s is a function. Another way to represent functions are by tables and graphs. You've probably seen this quite a bit in your lifetime of taking math classes. When we use tables, we usually have two columns. We usually have one for our x values and then one for our output. Remember, we're dealing with function notation, so it's not going to be x and y. Our relation is r, and therefore it's x and r of x. So when you put in a negative 1, you pop out a 2. When you put in a 1, it pops out a 3. And when you put in a 5, pops out a 2, and a negative 1 and a 3. It's totally okay. This is a relation, not a function. For s, same thing. We have our x values and we have our s of x values. Negative 2, 1, 0, 2, 2, 1, negative 1, negative 3. So that's in a table format. Now, if I took each one of these tables and plotted it on a Cartesian plane, which is this, cross, and you've got the 4 coordinates, and I plot these points on the graph, I'm going to get negative 1, 2 is right here. 1, 3, right here. 5, 2, right here. And negative 1, 3 is right here. Okay, that's just plotting the point. So I can represent this relation as a plotted graph. Likewise with relation s, who happens to be a function, negative 2, 1, 0, 2, 2, 1, and negative 1, negative 3. I can also plot those on the graph. Now, if I do not connect those dots, that's what's called a scatter plot, and therefore it's just called scattering of points, so it's called the scatter plot. Another way to define a function is by equations. Now that's very similar to what we've already seen. So f of x equals 5x plus 3, that was defining it by an equation. So for example, let's start off with y equals x squared, y minus x squared equals 0. Because we want to put this in function notation, I want the function notation on one side and everything else on the other. Keeping in mind, we are going to replace this y with our function notation. So first things first, I want to get rid of that x squared by adding it to both sides. Now we show y equals x squared. Now we're going to replace the dependent variable with the function notation. Again, you can name this function anything you want. F, G, Q, just don't call it x because it would be weird where you have x of x. That would be a little weird. I'm going to call it f. And so f of x is x squared, or f of x equals x squared. So this is function notation. Now, given the value for x, we can solve for f of x. So let's say I'm going to give you the value of 3 for x. Then wherever we see an x, we're going to replace it with a 3. So f of 3 will be 3 squared. And because 3 squared is 9, our f of 3 equals 9. So our solution would be 3 goes in, 9 pops out. That would be our ordered pair. Now let's figure out if the equation defines a function. So we're going to have a equals 6x squared minus 3y plus 12. And we're going to solve this for y, because remember, we want to put this in function notation. And then we're going to play our little trick of, does every x go to a y and only one y? First things first, let's get rid of this 6x squared. I'm going to subtract 6x squared from both sides, and I get negative 3y equals negative 6x squared plus 12. Divide each term by that negative 3 so we can get y all by itself. Divide by negative 3, divide by negative 3, divide by negative 3, and we end up with y equals 2x squared minus 4. Now I'm going to change this into function notation, and that would just be something like f of x equals 2x squared minus 4. Now this is a function, because if you put in an x, it goes directly to a y. So I'm going to put it in 1, just for argument's sake. 1 squared is 1. 1 times 2 is 2. 2 minus 4 is negative 2. So if a 1 goes in, a negative 2 pops out. Now you might be wondering, wait a minute, what about negative 1? Negative 1 squared is 1. 1 times 2 is 2. 2 minus 4 is negative 2. But those were two different x's. 1 will only ever go to negative 2. Negative 1 will only go to 2. It's not going to go to 2 and 3 and 4 or whatever. It won't have more than one output value. Let's try a second example. Y squared minus x squared equals 4. Again, I want to solve this for y. So I'm going to move this minus x squared over by adding x squared to both sides. And I get y squared equals x squared plus 14. Now I don't want the y squared, so I am going to square root it. But if I square root this side, the left side, I need to do plus and minus on the right hand side. It's the rules. So I'm going to square root y squared equals plus or minus the square root of x squared plus 4. And now y will equal the square root of x squared plus 4, and it will also equal the negative square root of x squared plus 4. That's two ways of inputting to get an output. Okay, so not only, let's try 1 here. 1 squared is 1. 1 plus 4 is 4. This is the square root of 5 by putting in a 1. Put a 1 here. 1 squared is 1. 1 plus 4 is 5. This is a negative square root 5. So by putting in one value of 1, I've got two separate outputs. That means this is not a function. Now, evaluating a function is where you're going to be given a function and it's defined by an equation, and then you're going to be given a value that you replace the variable with, and then follow your order of operations in math to solve for the function value. Okay. For example, let's now say g is the function, and it's defined by the equation of y equals x squared minus 6x plus 8. Where the y is, I'm going to replace with g of x, the function g of the dependent variable x. So g of x equals x squared minus 6x plus 8. And we're going to do some calculations. We've got 5 calculations we need to do. The first one, we're going to evaluate what g of 3 is, then g of negative 2, g of 1/2, g of a plus 2, and g of x plus h. Let's do the first one. All right, so I'm going to cover up b because we don't need b yet. Wherever I see an x in this g of x equals x squared minus 6 plus 8, I'm going to plug in the value that we need to evaluate it, which is at 3. So g of 3 is going to be 3 squared plus 6 times 3 plus 8. Now, following order of operation, I need to do that squaring first. So 3 squared is 9. I have 9 minus 6 times 3 plus 8. Next is multiplication. 6 times 3 is 18. So I've got 9 minus 18 plus 8. And next, I am going to follow my order of operations still and do adding and subtracting from left to right. So I need 9 minus 18 is negative 9. Negative 9 plus 8 is negative 1. So when I put in a 3, a negative 1 pops out. Let's do g of negative 2. G of negative 2, everywhere I see an x, I'm going to replace with negative 2. So g of negative 2 is negative 2 squared minus 6 times negative 2 plus 8. Negative 2 times negative 2. Well, a negative times a negative is a positive, so that would be a positive 4. 4 minus 6 times negative 2 plus 8. Next, I'm going to do this 6 times negative 2, but there is a negative out here, and a negative times a negative makes a positive. So that's going to be 4 plus 12 plus 8. Following order of operations, I'm going to do 4 plus 12 is 16. 16 plus 8 is 24. So when I plug in a negative 2, out pops a 24. For C, g of 1/2. Now, I know a lot of you don't like to work with fractions, and I don't care if you use 1/2 or 0.5 here. It's up to you. I'm going to keep it as a fraction. Ultimately, if you start with fractions, your answer has to be a fraction. So even if you put in decimals to put them in the calculator, that's fine, but your end result should be a fraction. So you got to convert that decimal back over to fraction. All right, g of 1/2. 1/2 is pretty doable, so I'm going to leave it as a fraction. Wherever I see an x, I'm going to plug in that 1/2. So g at 1/2 is 1/2 squared minus 6 times 1/2 plus 8. 1/2 times 1/2 is 1 times 1 is 1, 2 times 2 is 4, so that's 1/4. Next step, multiply this 6 by 1/2. 6 times 1 is 6, divided by 2 is 3, so this becomes a negative 3. Now, because I am ending up doing some subtraction and addition, I have to have similar denominators, common denominator. And our common denominator is going to be 4. So I'm going to go ahead and change this 3 to find an equivalent fraction with a 4 as its denominator, as well as the 8. So off to the side, I just did some math and I said, oh, 3 times 4 over 4. 3 times 4 is 12. 1 times 4 is 4. For the 8, it's going to also be 8 times 4 over 4. So 8 times 4 is 32, and 1 times 4 is 8. Or sorry, 1 times 4 is not 8, it's 4. So now I have all of my values with the same denominator, and I can just do the math that's on top. 1 minus 12 is negative 11 fourths, and then negative 11 fourths plus 32 fourths is 21 fourths. So if a 1/2 goes in, a positive 21 fourths comes out. Wow, say that one 5 times fast. All right, D, little bit more complex. We're not only working with values here, we're working with letters as well, so variables. G of a plus 2. So wherever I see an x, I'm going to place a plus 2. All right, g of a plus 2 is a plus 2 squared minus 6 times a plus 2 plus 8. Now, following order of operation, I am going to expand this a plus 2 squared. I find it easier if I write it twice, and that way I can FOIL it and follow along. So a times a is a squared. A times 2 is 2a. 2 times a is 2a, and 4 times 4, 2 times 2 is 4. My brain's jumping ahead. Sorry about that. Now, just because I'm kind of focused right on this front part, I'm going to add like terms so I can combine this 2a and 2a. Now, you don't have to do that. You could go and distribute this -6 through, but I'm just kind of concentrating on that to simplify it as best as I can. So I'm going to go ahead and finish up this foiling, and that leaves me with a squared plus 4a plus 4. That's just for that squaring right there. Now the rest of it, I'm going to take this -6 and distribute, and I get -6a minus 12. Everything else is the same, right? A squared plus 4a plus 4 plus 8 was all the same from the previous step. I only did the distribution of the -6. Now I'm going to start combining like terms. Okay, so a squared and a 4a and a minus 6a is in minus 2a. A 4 and a minus 12 is a minus 8. And then I have that plus 8 there that I haven't done anything with yet. Now I'm going to finally combine my minus 8 and my plus 8, which is 0. And I get a squared minus 2a. So if an a plus 2 goes in, an a squared minus 2a pops out. Okay. A little bit more complex. Slow yourself down if you need to. Double check your work as you're going, because these things can get a little crazy. Now, last one we're going to focus in on is g of x plus h. Wherever I see an x, I will place an x plus h. Okay. X plus h squared minus 6 times x plus h plus 8. The same steps as before, I'm going to do it with this guy. I'm just going to try and slow down a little bit so I don't make any mistakes. First thing first, I want to write this out twice. Okay, I've written it out twice. Now I'm going to FOIL. X times x is x squared. X times h is xh. H times x is hx, but we can flip that around and say xh so it looks like this other one. H times h is h squared. The rest of the problem I'm just going to rewrite out. So minus 6 times x plus h plus 8. Combining like terms, just like I did before, I have one xh here and another xh here. That makes it 2xh. Ooh, those are hard for me to say very quickly. All right. So now I'm going to distribute this -6. -6 times x is -6x, and -6 times h is -6h. Now I'm looking to see if I can combine anything. This is x squareds. There are no more x squareds. This is xh. There are no more xh's. X squared, no more h squareds. This is just an x, no more x's. H, no more h's. So because of that, if you pop in an x plus h, it will pop out as x squared plus 2xh plus h squared minus 6x minus 6h plus 8. Whew! Now you might be wondering, why the heck would we ever do that? Well, it could be something as similar as a function that you use all the time. This function might represent the velocity of some object thrown up in the air. And if you know the weight of the object and the height you throw it up, you can just literally plug it into this final piece of the puzzle to solve. You wouldn't have to go through all the steps to get there. You would already just plug in what your x value is and what your h value is. That's the idea of it anyway. Looking at the graph, I've given you a function graphed as f of x equals x cubed minus 3x plus 4. And then I've given you a rectangle that goes from point L to P to N to M, and it makes a rectangle. And we want to find the area of this rectangle. Okay, that's not bad. But we do have to remember what the formula for the area of a rectangle is. The area of a rectangle is its length times its width. Now, I don't care if you call this length or width. I don't care. You can call this length and this width, or this length and this width. it doesn't matter in the long run because 2 times 3 is the same as 3 times 2. Okay, so I'm going to decide that my area of this rectangle is length times width, and I'm going to let my length be the line P to N, and I'm going to let my width be the line P to L. Now, I could have used L to M and M to N. That would have been fine too, but I'm just going to use P to N and P to L, primarily because I've got this point on the function that I can use if I didn't have enough information. Okay, so to do this, I need the length between P and N. Well, N sits at the x value of 3, and P sits at the x value of 2, and if I say 3, the P sits at 1, so if I say 3 minus 1, I get 2. So that length is 2. Now my width is going to be the y value at this point. Now if I did not have this 2 sitting out here and I had nothing sitting out there, I would have to definitely use that function to find the output value when I put in a 1. And because I would have had to have done that, that's what I'm going to do. But for your side, if you wanted to, that could be 2 minus 0, which is 2. So we know this is a 2. But I'm going to use that function value instead. So we know that it's sitting at the x value of 1. So if I plug in a 1 in this formula, in this equation, I am going to get out the value that corresponds with a 1 going in. So 1 cubed minus 3 times 1 plus 4. 1 minus 3 plus 4. 1 minus 3 is negative 2, and negative 2 plus 4 is 2. So it's a little bit overkill for this problem, but it does work because that point is on the function. Now that I know my length is 2, my width is 2, I can plug it into my formula, length times width, and I get 4. In fact, it would be 4 square units. And if it was inches, it would be 4 square inches. If it was yards, it would be 4 square yards. Now, with that said, challenge yourself to figure out the area of the rectangle that goes from P to T to S to N. And what you're going to do is ignore this. I may have drawn it incorrectly. Find out what the S value is by plugging a 3 into the formula, and you will find the height of S all the way up there. That's a good little challenge to give to yourself. See if you can figure out the area of this dashed rectangle, PNST. Now the domain is the function, or all the values of x that we are permitted to put into the function. It's the largest set of real numbers that if we put it into the function, they pop out real numbers. So what goes in as a real number has to come out as a real number. And because of that, we have a couple of rules that we have to abide by. First of all, division by 0 is undefined at this level of mathematics. Right now, we are not going to deal with division of 0. So if you have a fraction and the denominator is a 0, you're in trouble. All right, so we want to make sure that our denominators in our fractions are not 0. Secondly, any even root, like the square root, fourth root, sixth root, eighth root, we are not allowed to take the root of a negative number because it is not a real number. You might be aware of complex numbers or imaginary numbers, and those are wonderful, but they're not real numbers. Remember, a real number that goes in has to come out as a real number. So even roots, we are not allowed to take the even root of a negative number. So that's the second rule we have to abide by. Let's find the domain of a function. We've got a couple of functions that we're going to take a peek at. f of x equals 1 over 1 minus x squared. G of x equals the square root of x plus 1. H of x equals 1 over the square root of x minus 1. And P of x equals the square root of x squared minus x minus 6. And we want to kind of look at these rules and see what's the possibility of our function breaking down. For the first one, the possible breakdown is that it's in a fraction, and we don't want this denominator to be a 0. So let's look at the solution here. Because division by 0 is not permitted, what values cause x in the denominator to equal 0? So we're really focused on this denominator. The rest of it does not matter. All right, so 1 minus x squared, when is it 0? I'm going to factor this. You could have moved the x onto one side and then take the square root, but I've chosen to factor this. And I get 1 minus x and 1 plus x equals 0. Using my zero factor property, I'm going to break these apart, set them each to 0, and solve each one independently. Looking at 1 minus x, I'm going to subtract 1 from each side. And I get negative x equals negative 1. But I don't want that negative in front of the x, so I need to divide by 1, negative 1. So when I divide by negative 1, that cancels out the negative on top, and I get x equals 1. So when x equals 1, we get 1 minus 1 squared equals 0. So if this is 1 squared, that's 1. 1 minus 1 is 0. That causes a problem here in the denominator. So we don't want to include 1 in our domain. We got to toss it out because it's, in essence, bad. Now, looking at the second way, we have 1 plus x equals 0. I'm still going to subtract 1 from both sides of the equation, and I get x equals negative 1. Now let's test it. Let's put a negative 1 in here. Negative 1 times negative 1 is 1, and 1 minus 1 is indeed 0. So we have to toss out x equaling 1 and x equaling negative 1 because both of those cause the denominator to become 0. But we can use any other number besides those two. Those are the only ones that will force it to be 0. And therefore, in set notation, it's the set of all x values such that x does not equal negative 1 and x does not equal 1. In interval notation, we get all the way from negative infinity all the way up to negative 1, but don't include it, union with the middle stuff from negative 1 to 1, but again, don't include those endpoints. And then finally 1 to infinity, and you don't include the 1. So interval notation, set notation. On to the second function, g of x equals the square root of x plus 1. Now, as it turns out, we don't have a fraction, so we don't have to worry about any x's in the denominator or anything to set off our denominator to be 0. But this is a square root, which is an even root. So we do not want any value on the inside to be equal to a negative value. And because of this, we have to be very aware of what values of x cause this radicand, that's what this is called, the radicand to be negative. So I'm going to pull out that, and I say I don't want this thing to take the square root of a negative number, and I'm really only worried about what's inside not being negative. So x plus 1 must be greater than or equal to 0. 0 is okay, negative numbers are not. And I'm going to solve this. So let's subtract 1 from each side. X must be greater than or equal to negative 1. It cannot be negative. It cannot be negative 2, cannot be negative 3, because that would make this be negative. Negative 2 plus 1 is negative 1, and we do not want to take a square root of a negative number right now. We're in the real numbers, not imaginary numbers. So our domain is anything greater than or equal to -1. In set notation, it's the set of all x's such that x is greater than or equal to -1. In interval notation, it's -1 to infinity and a square bracket to include the -1. Let's take a look at the next problem. All right, C. H of x equals 1 over the square root of x minus 1. Well, we not only have one problem, we've got two here. We're in a fraction, and the x is down in the denominator, and then on top of it, we've got a square root as well. So we want to be mindful that our denominator doesn't want to be 0, can't be 0, and the square root of a negative number is also in our heads to deal with. Now, our square root, this inside part, shouldn't be negative, and additionally, because it's down in the denominator, it shouldn't be equal to 0 either. Now, if we're negative, I could be x minus 1 is greater than or equal to 0. But remember, this cannot equal 0, so we're going to remove this equality part and just go for x minus 1 must be greater than only, not greater than or equal to, 0. Now I'm going to solve for those values. We're going to add 1 to both sides, and we get x is greater than 1. Now let's try it out. If x is strictly greater than 1, if I put a 1 in here, 1 minus 1 is 0. The square root of 0, totally permitted, is 0, but the problem is it's down in the denominator. Uh-oh, bad. But the moment I hit even slightly above 1, let's say just 1 for 1.1, for example, 1.1 minus 1 is 0.1. The square root of 0.1 is a real number. Off the top of my head, I don't know what it is, but it is a real number. All right. So our domain is all the set of all real numbers such that x is greater than 1. And then very similar to before, but we're not including the 1. So 1 to infinity, but not including it versus including it up here. That little equal makes it a square bracket. Greater than just makes it a parenthesis. All right, D. P of x equals the square root of x squared minus x minus 6. Now we need to take in consideration, this has no denominator, so I'm not worried about the 0. I am worried about this radicand being negative. All right, so I'm worried about it being negative, and I actually don't need this square root marker, so you can just ignore it. I drew it, but you don't have to be, you don't have to have this consideration of the square root. So we want to test to see x squared minus x minus 6 has to be greater than or equal to 0. It can be 0 because it's not in the denominator. I am going to factor this, and I get x minus 3 times x plus 2. Now I'm going to try and figure out, okay, well, there's going to be times where when I multiply a positive number by a positive number, I get a positive. That's cool, allowed. Negative times positive is a negative. Positive times a negative is a negative, and a negative times a negative is a positive. Positive times a positive is a positive. So it's only the circumstances where it's a negative times a positive I'm going to be in trouble. So to do that, first I'm going to solve x minus 3 equals 0, x plus 2 equals 0, and I'm going to find what's called critical values. So when I do that, I get x minus 3 equals 0 is going to be x equals 3. My other critical value, x plus 2 equals 0, it's going to be x equals negative 2. So my critical values are 3 and 2. So if I was to put that on a number line, I'm looking for all those instances where x minus 3 times x plus 2 gives me a positive value. Because these are my critical values, I'm going to have to test some value in each region. I'm going to have to test something over here, something in the middle between those two values, and something above this last critical value. You may choose any value you want to test. It's up to you. As long as the value is somewhere in those three regions, one number each to test. So I'm going to test this not once, not twice, but 3 times to figure out which regions are good. First region is anything below a -2. Just for argument's sake, I'm going to say x is -4. That's the value I chose. You could have chosen anything else you want. Wherever there is an x right here, I'm going to plug in -4. -4 minus 3 times -4 plus 2. -4 minus 3 is -7. -4 plus 2 is -2. -7 times -2 is 14. More importantly, it's positive. And in this sense, anything I would have chosen on that side, on the left side of -2, would be positive. You try it with a different value. You will get a positive value out of there. Next region that I want to test is in between -2 and 3. And for me, the value that's fun to use is 0. It's easy math, so I like 0. Okay, 0 minus 3 times 0 plus 2. 0 minus 3 is -3. 0 plus 2 is 2, and therefore -3 times 2 is -6. More importantly, I'm only worried about the symbol. The symbol is negative, and in fact, if I would have chosen any value in this region, it would pop out negative. Try another one. It will work. Any value in that region will turn out to be negative. Lastly, I need to test something on the right side of 3. So I'm going to go ahead and test 5 is my value. Of course, that's on the right side of 3. Plugging in a 5 everywhere, I get 5 minus 3 times 5 plus 2. 5 minus 3 is 2. 5 plus 2 is 7. And 2 times 7 is 14. More importantly, it's positive. I don't care that it's 14. I care that it's positive. So here's what we've got. Anything below a -2 is good because it popped out positive. Any value between -2 to 3 is bad. And any value above 3 is good. And remember, we're allowed to be 0, so here's how we're going to write it up. The domain are all the x's such that x is less than or equal to -2, that's this one, and x is greater than or equal to 3, that's this side. In interval notation, it's going to be everything -infinity to -2, including it, unioned with 3, including it, all the way up to positive infinity. Range of a function is that output that goes in after you've decided what your input can be. Remember, we sometimes have limitations on what our input can be, and that might have limitations of what our output can be. So let's suppose that we have y is the range of our function, and we have at least one solution. Otherwise, we're going to be problem. We're not going to have anything to put into our function. So we're going to say we have at least one function. So let's find the range of a function. Let's let our f of x be x squared with the domain of x from 3 to 5, including 3 and 5. Now here's the thing. We are limiting what our domain could be. So we are going to limit what our range can be, of course. All right. And we want to answer a couple of questions. Is 10 in the range of our function? Is 4 in the range of our function? And then we're going to find the whole entire range of our function. So let's take a peek, see at 10. Now, if 10 is in the range of our function, then it should be one of our outputs. So f of x must equal 10 if it is indeed in the range. But f of x is also x squared, so we can rewrite f of x as x squared. Now I'm going to solve for x. I'm going to take the square root of both sides, but I'm going to be very careful on the right-hand side that I'm going to do plus or minus. So the square root of x squared equals plus or minus the square root of 10. Okay, so x equals plus or minus the square root of 10. Now I'm going to leave it like that, but if I was to throw that into a calculator, 10 is a little bit above 9, so this whole value is just a little bit above 3 because the square root of 9 is 3. So I know this is a little bit above 3. And because when x is the positive square root of 10, it does fall within our domain, right? It goes from 3 to 5, and we're allowed any of those values within that range. I'm just going to correct it just like that because we can be 3 and 5 as well. Therefore, it's in the range. Therefore, this is good. But we have to look at that negative one as well. Now, negative square root 10 is a negative 3 point something, which is a lot less than 3. And therefore, it's not in the range. But here's the thing. As long as 1 works, 10 is in the range. And because the positive 1 worked, it is in the range. Only one of them has to work. Now, let's look at if 4 is in the range. Now, again, we're going to play the same trick. Since f of x equals 4, we can rewrite f of x as the defined version of it and say it's x squared. We're going to take the square root of both sides. Don't forget that plus or minus on the right. And we get the square root of x squared equals plus or minus 4, the square root of 4. Now the square root of 4 is 2. So that leaves us with x equals plus or minus 2. Now as you see, neither one of them work. Negative 2 is definitely less than our boundary of 3 for our domain. And 2 is also less than 3. And therefore, neither one of them are in the range of f. Those are not x values we are permitted to put in. Neither one of them are in the range. Let's go ahead and find the full range of our function f. Okay, we know f of x equals x squared. We could write this up as y equals x squared. We're looking for our outputs when we put inputs in. Now, because x can only be values from 3 to 5, including 3 and 5, 3 is our lowest value, 5 is our highest value, and because we're squaring it, the smallest value I will get out, my output, is when I square the smallest number. And the largest number I will get out of my function will be the largest number that I can put in squared. All right, I know there's a lot of words, but let's see it in action. Y is going to be 3 squared. 3 squared is 9. That's the smallest number that can pop out of my domain. 5 squared is 25, and therefore that's the largest number that can ever pop out because I can't go higher than 5. And since this is squaring, it's smallest number to largest number. So my range is from 9 to 25, including those. Is that kind of easy peasy, right? Sometimes we got to think about it a little bit more if we're dealing with negative numbers or not these squaring and things like that. But this was pretty much straightforward. Throw it in there and see what your low value is and your high value. All right. Graphs of function are another way of evaluating functions. We're looking at our ordered pairs of x and f of x such that x is in our domain of our function. Now we have a rule that we can abide by when we have a visual representation of a function, which means a graph. If no vertical line intersects the graph of a relation at more than one point, then the graph of the relation is a graph of a function. Sounds like a lot of words to mean something very simple, which math usually does, right? So here we've got some graphs here. I'm going to take a vertical line. This is the best vertical line I have, is a ruler, and I'm going to play the vertical line test on these graphs. I'm going to start with A. A is a scatter plot, but I am going to hopefully hold my ruler vertically, and I've got some lines I get to follow. So let me see if I can brighten it up a little bit. There we go. Hopefully it's not too bright. And I'm just going to push my ruler along with a vertical line through my graph. So right there I hit 1 point. I hit another point. I hear 1 point, 1 point, 1 point, 2 points. Okay, I'm dead in the water. This is no longer a function. It was a function up until that point, but all points have to meet this vertical test line. It's not that I can just throw these points out and all of a sudden it becomes a function. No, this is part of the graph, and because it fails and hits 2 points at the same time, it is a relation, but it is not a function. All right, so a relation, but not a function. Let's try the other one. And again, I'm kind of going backwards as I normally would. I'll try and do it this way. It's a little bit harder the way I have it set up on my desk, but let's see. See if I hit more than 1 point at any time. Okay, I've got some of the graphs showing here, and I've also hit, in fact, I'm hitting 3 points. I'll move over a little bit so you can see it even better. I hit a point here, here, and here. And the moment I hit more than one, actually right at that point, along with the point that's right up below it, I am no longer a function. So B is a relation, not a function. Okay, let's try C. I'll try and do my best to get it vertical. And I'm hitting 1 point. So far, still good. Still only 1 point. And all the way through, I hit 1 and only 1 point, and therefore C is a function. Now, let's try D. I'm hitting 1 point, 1 point, still 1 point. Okay, I turned back around and now I'm going down, but I'm still 1 point. Now I've turned back upwards, I'm still 1 point, and now back downwards, and I'm still 1 point. And I've hit 1 point all across, and therefore D is also a function. So A and B are relations, C and D are relations, but they are also functions. Vertical line test. I think it's the easiest way to test to see if something is a function. You just run a ruler along, and if you hit more than 1 point, boom, it fails the vertical line test. Now there's some information we can get just from the graph of a function. First of all, we can figure out if a point is actually on the graph of the function. Secondly, we can figure out the domain and range just from looking at the graph. So let's take a peek see here. And I've got this graph right here. And my function is the red portion. It starts at point AB, so A on the X and B on the Y, and it goes up to C on the X and D on the Y, and it ends. Okay, so from A to C on the X, B to D on the Y. The X values that it can be is our domain. We are allowed to go from A, including A, all the way up to C, including C, so our domain is from A to C, inclusive. Our range is what areas were permitted on the Y, and it goes from B to D. And since we have B to D in a smooth curve, our range is D to B inclusive. Now we can also see, does this point EF, is that on our function? And just by eyeballing it, yeah, I can see that it's on our function. So point EF is on the function of F. Looking at the graph is really kind of simple to figure out where your domain is and your range is most of the time. Of course, there's those instances where it's like, what? Okay. Now, I want to... Got two graphs here. I'm going to cover up one while I reveal the other. Okay, so here we've got another graph, and I want to figure out its domain and range and see if the point that's on the graph is on the function itself. So here, my arrow goes all the way out, and it keeps going that way forever. And in fact, my arrow goes up this way forever. So it's going right and up forever. And the graph also goes down and left forever. And because it never stops, my whole entire x-axis is available to be in the domain, and the whole entire y-axis is totally available to be in the domain. So the domain of f is from negative infinity to positive infinity, and our range of f is negative infinity to positive infinity because of those little arrows. If it didn't have the little arrows and it stopped at a particular point, then it would be very similar to the first option. Now we want to see if CD is on our function. Well, is it on the red line? No, therefore it's not on the function. It is within the domain and range, but is not a solution for the function. It is not on the function. That's the difference here. Okay, now let me scooch this up some. Let's look at another graph. I have this graph where it starts at an open dot, goes up, so it starts at negative 2, 1, goes up to 1, 4, goes down to 2, 2, and then back up to 3, 3. Now, our domain are all the x's that it can be. It starts out at negative 2 and goes as high as 3, but it doesn't go beyond 3. I know there's some loop-de-doo there, but we are allowed to go from negative 2 to 3. And therefore our domain is negative 2, but not including it because there's an open dot, but including the 3, it's a closed dot. Okay, now our range has to do with our y values. Our y values start at 1, go up to 4, down to 2, back up to 3. Our lowest value was 1, but not including it, and our highest value was 4. Granted, we whoop-de-dooed right after that, but our highest value is 4. So our range is 1, but not including it, all the way up to 4. Now, our last graph is called a piecewise graph. There's a couple pieces to it. The first piece is this line segment from negative 3, negative 1 to 1, 1. The second piece of the graph is way up here at 3, 4, and it continues to the left and continues to the right indefinitely. Okay, let's look at the x values first. The domain. The domain can go as far left as negative 3, and then it stops at 1, and then it picks back up at 3. Okay. So our domain is from negative 3 to 1, and then 3. Our range. Okay, our range is where our y values are. So it goes all the way from negative 1 to positive 1, and then boom, it goes up to 4. So our range is going to be negative 1 to 1, and then the value 4. So here's our domain. It is negative 3 to 1, and then 3 to infinity, because it goes off forever to the right. For our range, it is negative 1 to positive 1, including those two. Those should be brackets around there. And then 4. And when we have just one value, it is in curly brackets to signify that it is a value. Okay. So yeah, piecewise, you'll have this jump. That usually means you'll have a jump somewhere in there, a little spacer or something. And yeah. All right. Let's examine the graph of a function. We're going to let f of x equal x squared minus 2x minus 3. And we're going to ask a couple questions. Number one, is the point 1, negative 3 on the graph of our function? We're going to find all the values of x so that x5 is on the graph of f. We're going to find all of the y-intercepts, and we're going to find all the x-intercepts. All right, first of all, is the point 1, negative 3 on the graph? The easiest way to figure this out is let's plug in 1 and see if the negative 3 pops out. So, does f of 1 equal negative 3? So let's plug it in and see. F of 1 is 1 squared minus 2 times 1 minus 3. 1 squared is 1. 2 times 1 is negative 2, so 1 minus 2 minus 3, negative 1 minus 3, and so we get negative 4. Now, Negative 4 does not equal negative 3, what we were expecting, and therefore this 0.13, it's not on the graph of our function. It was not the expected output. We got a negative 4 and we expected a negative 3, or we wanted it to be negative 3, and therefore because 1 negative 4 is on the graph, 1 negative 3 is not on the graph. All right, B. Let's find all the values of x so that when we put in a value for x, it pops out a 5. So we want f of x to equal 5. That means 5 equals x squared minus 2x minus 3. I'm going to set this equal to 0 so I can use my zero factor property. So I'm going to subtract 5 from both sides, and we get 0 equals x squared minus 2x minus 8. I'm going to factor the x squared minus 2x minus 8, and I get x minus 4 times x plus 2. I'm going to use my zero factor property to break these apart to see which values of x we get. Okay, for x minus 4, we're going to add 4 to both sides, and we get x equals 4. For x plus 2, I'm going to subtract 2 from both sides, and I get x equals negative 2. That means when I plug in a 4, a 5 pops out. When I plug in a negative 2, a 5 pops out. Because remember, that's how I had it set up originally. You can plug those in and double check. Okay, so let me try 4. 4 squared is 16 minus 2 times 4, which is 8. So 16 minus 8 is 8. 8 minus 3 is indeed 5. Let's try negative 2. Negative 2 squared is 4. Negative 2 times negative 2 is 4. So 4 plus 4 is 8 minus 3 is 5. So both of those answers work. I plugged in the 4, it popped out a 5. I plugged in a negative 2, it popped out a 5. Let's find all the y-intercepts. Well, when we have a y-intercept, that means x equals 0. So what I'm going to do is I'm going to plug in f of 0. So f of 0 equals 0 squared minus 2 times 0 minus 3. All right, that gives me minus 3, negative 3. So one of our y-intercepts, or our only y-intercept, is when x equals 0 and a negative 3 pops out. So we either say y-intercept equals negative 3, or we give the point location of 0, negative 3. The next thing we want to do is find all the x-intercepts. When we're looking for x-intercept, that means our f of x equals 0. In other words, our y's equals 0. Okay, plugging f of x equals 0 in there. Now I'm going to solve for all values that cause that to be 0. X squared minus 2x minus 3 factors into x minus 3 times x plus 1. Using zero factor property, I'm going to break those apart and I'm going to solve each one of them. So adding 3, we get x equals 3. Subtracting 1, I get x equals negative 1. And therefore my x-intercepts are 3 and negative 1, or we put them in the point format and say 3, 0 and negative 1, 0. Now let's summarize some of the facts that we've done here. Main facts of a function is usually described in one of these ways. 1, usually have a correspondence diagram. 2, a set of ordered pairs. 3, a table of values. 4, an equation of a function. 5, a scatter plot or graph. And then y as a function of x when you're using words. Our input is x. It is our first coordinate when we have ordered pairs. It is our independent variable, and it is our domain. Our y is our output. It is our second coordinate of any ordered pair. It's our dependent variable, and it is our range. Let's focus on building functions. There are some word problems in the book, and I really want you to look at the language of the book. I've pulled out some very important formula here, and let me turn to the page of the book. Okay, so All right. Building functions. We have this level of drug in the bloodstream, and when you take a dose of medicine, the drug level of the blood goes up quickly and it reaches its peak. We're going to call that C max, so it reaches its peak. And then as your liver or kidney decides to remove the drug from your bloodstream, your drug level drops until it gets to this trough, which is at its C minimum. This is its minimum concentration. The ideal dose should be strong enough to be effective without causing too many side effects. We start by setting up lower and upper limits of the blood levels, and then we figure out pretty much how much drug we're going to use. Now in this example, we're going to use this drug, and it's called a statin, and along with proper diet and exercise, it prevents heart attacks and strokes. Now, the important part is, here's what I've pulled out. The statin has a bioavailability of 30% that has been prescribed for this guy, Boris, to treat his cholesterol levels. He is to take 20 milligrams daily. Every day, his body filters out half of the statin. Find the maximum concentration of statin in the bloodstream on each of the first 10 days of using the drug, and then we're going to graph the results. Okay. So, here we go. On day 1, he takes a 20 milligram dose, and 30% is bioavailability. That means his body's going to soak in, leave 30% in his bloodstream. And every day, so that's 20 times 0.30, which is 6 milligrams. That stays in his system. On day 2, half of his previous day plus day 1 will be in his system. So again, we take what was in his system the day before, 6 milligrams. We're going to half that, and then we're going to add the first day 6 milligrams. So we get 3 plus 6 is 9 milligrams. And we're going to repeat this for day 3. 1/2 of the previous day plus day 1. So 1/2 of the 9 milligrams from the day 2 plus the original 6 milligrams. So 4.5 plus 6 is 10.5 milligrams. And we keep doing this. This is what's called a recursive function. The recursive function takes what happened before and does something to it, and what happens before and keep on doing it. One of the most famous recursive function is Fibonacci, where you start with either 0 or 1, or 1 and 1, and you take the two previous numbers and you add them together. So let's say we start with 0 and 1. To get the very next number in the sequence, we have to take the two previous numbers and add them together. So 0 plus 1 is 1. The next number that goes here, I take the two previous numbers, 1 and 1, and I add them together, and I get 2. 2 plus 1 is 3. 3 plus 2 is 5. 5 plus 3 is 8. 8 plus 5 is 13. So there's no way to get the next number without knowing what happened before it. This is the idea of what's a recursive function. So on day 0, he didn't take anything. Well, he doesn't have anything left in his body because he hasn't taken anything. On day N, he's going to take 1/2 of the previous day plus the 6 that was originally from taking the first dose. This is what's called a recursive function, because you got to know what happens before it before you know what happens after it. So writing it as this recursive function, I can say, okay, at 0, it equals 0. At day 1, it's half of the day before, 0 plus 6. So I've got 0 plus 6 equals 6. C2 is going to be half of what came before it, half of 6 plus 6. And we get 9. Next, on the third time, we take what we did before, which is 9, take half of it, add 6, we get 4.5 plus 6 is 10.5. And when you keep doing this, you reach up to like day 10, for the next day 10, it's C9 plus 6, and you get 11.989. And when you graph this, your max reaches like really nearly 12. but it doesn't hit 12. This number, the number before it was 11.977. The next number is 11.989. The next number will be smaller and smaller and smaller until you'll hit this line of 12 and you won't go past it. Okay, so that's the graph of it. And I just graphed a few 1, 2, 3 for the days just to show you where it was on the graph. All right, let's hit up our last example in this section, cost of fiber optic cable. Now this company wants to connect 2 points on opposite, let's start with deciphering this problem. There are 2 points, A and B are on opposite sides of the bank of a straight river that's 500 feet wide. So I'm just going to draw myself a little picture here. A and B are directly opposite of one another, and there's a gap of 500 feet. The river is straight. All right, next. Point D is on the same side as B, but it's 1,200 feet upriver from B. So I'm going to pretend this side is upriver. So I'm going to throw D onto my little graph there. And I know it is 1,200 feet up the river from B. So this distance from B to D is 1,200 feet. The distance between B and A is 500 feet. Now here's the problem. The local internet cable company wants to lay fiber optic cable from points A to D. But it costs 5 feet per foot if we go underwater, and only 3 feet per foot if we do on land. So staying on land is going to be cheaper for us. And because we're going to have to suck up some of the costs going underwater at the shortest at 500 feet and then 1,200 feet. So I'm looking for some point in between B and D to kind of go underwater and then go above water. And it will hopefully save us some money versus going straight across then all the way down. The distance from A to B then B to D is longer than going straight from A to D, but the cost would be more because we have to go underwater. So we're going to create this point P that's somewhere in between B and D. I don't know quite where. It from B to P is some distance, and from P to D, well, I know the whole entire distance was 1,200 feet. So let's say that X is 100 feet. Then 1,200 minus 100 would be the remaining 1,100 feet. And if X was 200 feet, then this would be 1,000 feet because I know I just subtract out whatever X is. So this setup is pretty nice. Now here's the thing. I need to find the length from A to P and then P to D. This is underwater. This is on land. Now, once I solve for this point, I can figure out X. Now, from A to B to P and back to A creates a right triangle. So just to bring back into your head, Pythagorean theorem, A squared plus B squared equals C squared. So this distance C, the hypotenuse, aka the diagonal of the triangle, the right triangle, is going to be the square root of A squared plus B squared. Okay. Now, here's my solution. All right. I need the distance from A to P. And I need the distance from P to D. Okay. A to P is going to be the square root of 500 squared times x squared. That's the Pythagorean theorem in action. P to D, well, is 1,200 minus x. So I have everything that I need to build a function. The cost is going to be 5 times the distance underwater plus 3 times the distance over land. So it's going to be 5 times the underwater portion, A to P, plus 3 times P to D portion. Now I'm going to replace what I had for AP in with AP and replace PD with what I have for PD. So 5 times the square root of 500 squared plus x squared plus 3 times 1200 minus x. And that's our equation. Now, given minimally AP has to be 500 feet. So let's say it's 700 feet. I can put in, well, if this is 500 feet and let's say this is 200 feet, then I know that's 1,000 feet. So x is 200. So if I put 200 here and 200 here, I'll be able to figure out the cost. If this is 300, I'll be able to say, oh, 300 and 300 and figure out the cost if indeed this portion is 300 feet. And that's how I'd figure out the cost. Now, functions play a very important part in economics. This is really economics of a business, but in general, economics. There are 3 things I want to talk about with economics. There's a break-even point, earning a profit point, and of course, taking a loss. That's the thing we want to avoid. Now, if X represents the number of units that we can manufacture, P is going to represent the price in dollar of each item sold. So let's say we're manufacturing pencils, and P is going to be the price at what we sell the pencil. X will be the number of items that we actually make. Then the cost function, which is C of X, of producing those X number of items is going to be C of X equals the variable cost plus the fixed cost. This is what's called the linear cost function. The variable cost, it's going to cost us so much money to make just one pencil. And every time we make that pencil, it costs us that amount. That's the variable cost. The fixed cost might be, well, how much lights do we have to turn on, and how much salary that I'm going to have to pay my managers. Whether we make a pencil or not, I still have to pay those managers. Or maybe it's keeping the water on. Those are what's called fixed costs. Whether I create a pencil or not, I still have to pay those fixed costs. The variable cost is dependent on how many pencils I actually make. This is what's called the linear cost function. So B is the fixed cost, the cost no matter how many items are produced, and A is the cost per item. It's also called the marginal cost. So A is the marginal cost, and that marginal cost times the number of units is going to be our variable cost. Another function we work with for economics is called the linear price demand function. Suppose we have X number of items that can be sold, meaning what's demanded, at a particular price. Keep in mind that we have a couple of equations. One is the price, P of X, which is dependent on the price as a function of X. And I'll talk about the M and the D in a second. Or we're dealing with the number of items along with as a function of the price, and again, the N and the K. So this X is the number of items. This P is the price. Same thing, this is the price function of X, and this is the number of items as a function of price. Now keep in mind, higher price means fewer items sold. Let's take that pencil. My pencil is just a pencil. I think I have a pencil running around here somewhere. I've got lots of pens. All right, I've got a pencil. Here is my pencil. My pencil is not fancy. My pencil is not anything to you write home about. It is just a pencil. It's a mechanical pencil, but it's still a pencil. If I sold this pencil for a penny, I would probably sell a lot. And if I sold this pencil for $100, I probably wouldn't sell very many, right? So the higher the price, the fewer that are sold. This doesn't mean there's some fluky thing out there that, you know, somebody famous online says, ooh, this is a great pencil, and then idiots go out and buy it just because some famous person said it was great. Whatever. Probably shouldn't talk like that, but it's true. Sometimes you get peer pressure to buy something and it's junk, but whatever. Let's just say you got no peer pressure to buy this item. You wouldn't buy it for $100. Maybe you would buy it for $1.50, but you wouldn't necessarily buy it for $100. That is the price demand function. The demand dictates really what the price could be. The higher the price, the fewer items sold. These variables of M, D, and K actually depend on the situation, and normally they're given to you. So this M and D, N and K would be given to you as numbers, not necessarily constants. Not necessarily variables. Now there's a price supply function, and it's going to say, well, supply of X or G of P. So it's either a function based on X, the supply based on the number of items, or the gross of the price. Keep in mind, higher price results in more supply. So the higher the price of the item, the more supply you want, because you want to be able to sell lots of items. Now let's get down to what really is going to hit you hard, which is the revenue function. Revenue is the amount of money that you get in by selling your objects. But you have to take away the cost of the item to be able to make a profit. So revenue minus cost equals profit. Our revenue function is R of X. Our cost is C of X, and our profit, we're going to write it as a function P of X. P for profit, R for revenue, C for cost. It is all based on the number of items we sell, or I should say all the value, the number of objects that we manufacture and can be sold. Manufacturing company will take on one of three situations. To have a profit, well, your profit function has to be greater than 0. Your revenue has to be greater than the cost. To break even is when your P of X equals 0. That means your revenue equaled your cost. That's your break even point. And you will suffer a loss if your revenue was less than your cost. Then your P of X value will be negative. So if it's greater than 0, you will have a profit. If it is 0, you're at a break even. And if you are below 0, negative, you will suffer a loss. At least your company will. Let's talk about finding that break-even point. Metro Entertainment Company spent $100,000 on a production cost for its off-Broadway play, Bride and Prejudice. Once the play runs, each performance costs $1,000 per show, and the revenue from each show is $2,400. Using X to represent the number of shows, we want to find the break-even point. Here are things that are going to make it a lot easier to find this break-even point. First of all, we need to find the cost function, and then we're going to find the revenue function, and then we're going to find the profit function. And then once we get to this point, we're going to figure out the number of shows for the break-even point. Now, okay. First of all, cost function. Okay, our cost function was our variable cost plus our fixed cost. Now it costs us $1,000 for every show, and we're going to allow X to be how many shows that we run. So 1,000 times X plus the $100,000 that they initially laid out to create this play is going to be our cost function. Next, our revenue function. How much money will we earn? Okay, revenue per show times the number of shows. So our revenue per show was $2,400 times the number of shows. We don't know how many number of shows we're going to do. That way it's still X. This X is exactly the same X here. Now if you remember, our profit function was our revenue minus our cost. So let's throw that in there. Revenue, 2,400X, minus our cost. Keep in mind, it's the whole entire cost function. I am going to distribute this negative through, and I get 2,400X minus 1,000X minus 100,000. Combining my X's, I get 1,400X plus 100 minus 100,000. Now this is where we're going to find our break even. Our break even is when this P of X equals 0. And therefore, I'm going to set this function up to equal 0 and solve for x. Okay, I'm going to add 100,000 to both sides. I get 100,000 equals 1,400x. Divide by 1,400 on each side. I get x equals approximately 72.4 shows. Now, we need to run at least 71 shows to break even. We will actually start making a profit once we run the 72nd show. But we need to run at least 71 to break even. Okay, we have made it to the end of 2.4. I'm really proud of you guys for sticking through it. I know it's a lot of math. So hang in there. If you have any questions, please reach out to me. I am always here for you. So until next time, be seeing you.